Okay, so we just finished off chapter 3, techniques of derivatives. So using a lot simpler methods of doing derivatives besides using the formal definition and using limits. And chapter 4, we're going to get into graphing using properties of derivatives and limits. And so 4.1 is where we're going to start, which is on extreme values of a function. Okay, so basically, what this is telling us is if you have some function, so let's just look at some graph. And we're given that it is defined everywhere on some interval. So looking at my graph, it's defined, it's continuous everywhere, there's no jump, it's differentiable everywhere. And if let's choose some interval A to some interval, maybe let's say B. Within that interval A, B, our function f of x, there's going to exist what they call relative extrema or absolute extrema. Actually, it really depends on what book you're using, different terminology. So yours uses extreme values or global maximum and minimum. Okay. So basically, looking at f of x on our screen between a and b, it's a continuous function. And so because of that, between a and b, we're going to have a maximum and a minimum, an absolute max and an absolute min that has to occur. And that absolute max or absolute min could occur in between a and b, or it's possible that it could occur on the endpoint itself. So looking at this, in between a and b, I can see that I have a max right here. So this is called a local max. And right here, this one would be a local min. I'm not sure if this is an absolute one or not, and we'll look at this in a second. And so let's look at our n values and what values that hits on our graph. And so if I look at where the y value when x equals a, I get a value about right here. And if I look at when x equals b, my y value hits about right here. And so it looks kind of close between x equals a and my local minimum, which y value is smaller. And so if I look at this, and I look at my y value, so right here, this is f of b. I'm sorry, f of a. I'm looking at b while I do it. And if I look at this value, maybe let's call it c. And so if I look at my y value, it looks like that y value is bigger than my y value when x is a. So looking at this, we have what are called local max, local mins, and we also have what are called global max and global mins. If you look at this graph, though, that the highest point is occurring, and maybe we can call that something different, maybe D. And so I can tell that f of D is a, I'm going to have to get used to saying this because I've never called it global before, is an absolute or global maximum. Of f of x on the interval where X is between A and B and including. Okay, so notice if you look back at my graph and we didn't limit that between A and B, notice that f of X continues to rise as X goes to infinity. And so that would not be a global maximum if I had changed my domain here. And so here, my global minimum is occurring when at an endpoint. So f of A is the global minimum. Okay, so what we really are going to do when we're trying to find, and we're not given the picture, we're given our function, and we're trying to find what the global max and global min are. If we're given a closed interval, like we were just given here, and our function is continuous and differentiable on that closed interval, then a global maximum and global minimum have to occur. It can either occur at a max or min, or at one of the end values of our domain. So the question is, how do we figure out what, by looking at the equation or given the equation and not looking at the graph, where maybe a local max or local min would occur in between? So what did we know about the tangent line when we had max or mins on our graph? So recall the tangent line was equal to 0. So let me pull a problem out of the book and let's look through that. Okay, so let's say that we're given that f of X is equal to X squared minus 1. And we're given that our bounds are between -1 and 2 and including. So -1 is less than or equal to X. Which is less than or equal to, what did I say, 2. Okay. And so it says find the absolute. So now here it's saying absolute maximum and minimum value of each function on the given interval. And graph the function. Identify the points on the graph where the absolute extrema occur. And include their coordinates. Okay, so hopefully you guys already know what that graph looks like. X squared minus 1, y equals x squared minus 1. So it's a parabola. You can tell it's already in vertex form. It's just shifted down the vertex at 0, 0, down 1. And so just in looking at this, I can tell that we have a minimum, because the graph's facing up, x equals 0 and y is -1. But let's use calculus. Okay, we also know f of x equals x squared minus 1 is a continuous function everywhere because it's a polynomial. And so we want to figure out where our tangent line is equal to 0. Or the slope of our curve is equal to 0. And so first thing that you want to do is you want to find the derivative. And so if we look at the derivative of f of x, we have 2x. And so it's pretty easy to see that 2x is equal to 0 when x is equal to 0. And we need to figure out what is happening at our n values and at this number x equals 0. And so we want to plug in, you always want to plug in the n values of your interval when you're looking for absolute max and mins. And so if we plug in -1, and you're plugging this back into the original function. So sometimes we're going to see in this chapter that we're going to be plugging things back into our derivative function to see if our slope is increasing or decreasing. So if we plug in -1 back into our original function, we get -1 squared is 1, 1 minus 1. So that gives me a y value of 0. And then if I plug in x equals 0, because this is where a max or a min may occur, if I plug in 0 into my function, well, 0 squared minus 1 gives me -1. And then if I plug in 2, which is the end bound on the right of my interval, 2 squared is 4, 4 minus 1 is 3. Okay, so you're looking at the smallest value that occurs and the largest, smallest y value and the largest y value to find those absolute max and absolute mins. So this is the smallest y value. So this is our absolute minimum. And to find the absolute maximum, you're looking at the largest y value that we get. And so the largest y value that we receive back when we plug in either our n value or when our derivative was equal to 0 is 3. And so this is the maximum y value. So this is where the absolute min occurs. Let's just talk about it now because we're going to talk.
That's where the max occurs or the min occurs? Because you put min.
Max, the absolute max is going to occur at 3, and the absolute min is going to occur when y is -1.
So did you put min occurs or max occurs?
Sorry. Thank you. I see what you're seeing right here. Thank you. So max. Okay, so we want to graph it. It asked us to graph it, and we already talked that we knew what the graph hopefully looked like. And so we saw that here when x was 0, right, we had a point at -1. So x equals 0, -1. We saw when x was -1 that we had a point at 0. And we saw when x was 2, our other inbound, we had a y value of 3. And so looking at this, we have a graph Oops, sorry. Looks something like this. Okay, and so looking at that too, so you can tell, right, that at 0, the minimum value that you get is -1. And you can tell when x equals 2, the maximum value on that graph is 3. Okay, let's maybe look at another one. So same directions, but this time we're going to give that g of x. Actually, let me get in here. So I'm given that g of x is equal to the square root of 4 minus x squared. And we want to look at the interval between -2 and 1. Okay, so looking at this, sometimes it's helpful to look at the domain. First of all, is that continuous everywhere between -2 and 1? And so if we look at our domain of g of x, because it has a radical there, index is even, we can't have negative numbers underneath the radical and get back a real number. So we need to make sure that 4 minus x squared is greater than or equal to 0. Okay, so I don't know if you guys remember, but when you're solving nonlinear inequalities, that's where you kind of looked at what your, well, a couple ways we can do this, but you looked at what your critical numbers were, you factored it, found your critical numbers, test each side of your values to see if it was true or false. We can factor this as, it's a difference of squares, as 2 minus x, 2 plus x. So I'm finding critical numbers. And so 2 minus x is equal to 0 when x is 2. And 2 plus x is equal to 0 when x is -2. So as long as I have a positive number between -2 and 2, then I'm okay, this is continuous everywhere. And so if we looked at our number line between -2 and 2 and we chose a value that's in between, so choose any value in between and plug it back in here to see if it's true or false. So let's say I chose x equals 0. So g of 0 is equal to the square root of, oops, square root of what? 4. Okay. So we're okay. this is continuous in our interval, or this, which is g of x. Oh well. So g of x is continuous there. Okay, so I just work just to start our problem. And so now we need to look at the derivative. We need to find out where that was equal to 0, if it is. And then we also need to check our endpoints into our original equation. And so if we look at g prime of x, well, let's first actually rewrite g of x so that we can take the derivative. So this is the same thing as 4 minus x squared, all raised to the 1/2 power. And so looking at g prime of x, general power rule, bring down our power, we have 1/2 times the inside, which is 4 minus x squared, subtract 1 from our power. So that would now be negative 1/2 times the derivative of the inside. So derivative of 4 minus x squared is negative 2x. Clean it up a little bit. And so, oops, shoot. I don't know why I did that. We can bring down and we can cancel. So I notice I have a 2 in the numerator, I have a 2 in the denominator. I have a negative x left in my numerator, all divided by the square root of 4 minus x squared. And so I'm looking at, when is this equal to 0? Okay, so if we multiply both sides by the denominator, we're looking at when is negative x equals to 0. And so negative x equals 0, well, when x equals 0. Okay, so now we're just going to see what our y values are at our endpoints and at that critical number of x equals 0. Okay, so our n values were at negative 2 and 1. Critical number size x was 0. So if I put in negative 2 in here and we square it, we get positive 4. So you have the square root of 4 minus 4, which is square root of 0, which is 0. If we plug in 0 and wherever we see an x in g of x, we get the square root of 4, which is 2. And if we plug in 1 here, we get the square root of 4 minus 1, so square root of 3. So now the square root of 3 is less than 2. And so I know 2, my y value of 2, that is the max. And the minimum, so the y value that gets me the smallest, is at 0. And so this is the min occurs. So it also asked us to graph it. And we said we had -2 to 1. So x equals -2, we had 0. When x equals 0, we had 2. X equals 1, we had √3, which is between 1 and 2. Basically, you're going to get a semicircle with like, or not even a semi, a part of what kind of looks like a circle, semicircle. And that comes, it would come back down here. Okay, so just looking at the graph again, the min occurred when x equals -2, y is 0. And the min occurred when x equals 0. I said that opposite. You know what I meant, right? Max occurs at 0, 2. And min occurs at -2, 0. So what if you were given f of x is equal to 1 over x plus the natural log of x. And we're given it's between 0.5 and 4. Okay, so if you look at the domain, there's a couple places that you might have problems with f of x. Remember, we can't have values which set our denominator equals 0. And so for our domain, we know the domain x cannot be 0. I don't know why that's racing. But also, if you look at the term natural log of x, that piece, when you're looking at, by definition, x had to be greater than 0. Because of the natural log of x. And so we're okay because the interval we were given was between 1/2 and 4 and including. And so first thing that we want to do is we want to look at when is this equal to 0? Or sorry, we're looking at the derivative and finding when the derivative is equal to 0. So we need to find f prime of x. Well, think of 1 over x, right? If we had rewritten that as x to the -1 power, when we take the derivative of that, we bring down our power of -1 times x, and then we would subtract 1 from that power, which is -2, plus the derivative in natural log is 1 over what you're taking the natural log of, which is x in this case, times the derivative of what we're taking the natural log of, which is 1. And so if we rewrite this, this is equal to -1 over x squared plus 1 over x. And so we want to know, when is f prime of x equal to 0? Well, in order for me to add those, I guess I could just clear my fractions. So we can clear the fraction by multiplying by the least common denominator, which is x squared. And the only reason we can do this is because this is an equation and not an expression. And so x squared times 0 is 0 is equal to distributing my x squared. Well, x squared times -1 over x squared is -1. And then plus x squared times 1 over x is x. And so if we solve for x, we get x is equal to 1. Okay, so we got a critical number where our slope is equal to 0, where a max or min could occur, and we want to plug in our values into our original. In this case is f of x, to see what our y values are. And so we're going to plug in 0.5. We're going to plug in 4, and we're going to plug in 1. So if I do 1 divided by 0.5, which is 2, plus natural log of 0.5, this gives you approximately 1.31. If I plug in 1 wherever I saw an x, I get 1 over 1 is 1, plus the natural log of 1 is 0, and so that would give me a value of 1. If I plug in 4 wherever I see an x, I get 1 divided by 4, 0.25, plus the natural log of 4. So altogether, this gives me approximately 1.64. So the smallest y value I get back is 1. And so this is my absolute min. And the largest y value I get back is 1.64. So this is my absolute max. And then we wanted to look at the graph of that. So at 0.5, oh, that's not good. So we'll say that's 0.5. And at 0.5, we had about 1.31. I'm just estimating. At 1, we had 1. And then at 4, we had 1.64. It's going to come down. It's going to change direction and go up. And so this is what our graph of f of x would look like within those bounds that we were given. So there's some with product rules. There's some that have piecewise functions. So in the following, it says find the critical numbers or critical points and domain endpoints for each function. Then find the value of the function at each of these points and identify extreme values. Absolute and local. Okay, so a local max and a local min, those can occur at endpoints, or it could also occur at a place where you have dips or peaks on your graph. And so, let's say you had y is equal to x raised to the 2/3. And I'll make that bigger in a second. All times x plus 2. Okay, so first of all, is there some piece that we have to limit our domain to? So if we were to look at this domain, you're thinking to yourself, does that equation have any trouble spots? Do I have any variables in the denominator? Which the answer is no. And then if we have a radical, do we have negatives under an even powered radical? Well, if you look at x to the 2/3 power, recall that's the same thing as, so the denominator is what index of the radical. So this is the cubed root of x squared. And so we don't have any problems with a cubed root and the domain. And so the domain, in this case, we don't have any problems. And so it's all real numbers, negative infinity to infinity. So now we want to look at the derivative and finding our critical numbers. And so we need to look at when is y prime equal to 0? Oops. Or dy dx equals 0. And so we're going to have to use our product rule. And so using the product rule, derivative of x to the 2/3, bring my power down front. So I get 2/3 x. Subtract 1 from that, I get a negative 1/3 times the second function, x plus 2, plus the first, x to the 2/3, times the derivative of the second, which is just 1. Okay, so we can write that a little bit. And so we get y prime is equal to 2 all over 3 cubed root of x. That's 2 times x plus 2 in the numerator, plus the cubed root of x cubed, the cubed root of x squared. Okay, so notice critical values actually can also occur when when our derivative is equal to zero. Not zero, is undefined. And so notice that f prime, well, in our case, it's y prime. Y prime is undefined at x equals 0. I can't have 0 in the denominator. So that's going to be one of my critical numbers. If that was not part of my domain in my original function, that could have been where an asymptote is, but my original function, it was defined everywhere. So x equals 0 could be a critical number, and then we need to figure out when is this equal to 0. Let's clear our fraction or fractions, and we can multiply everything through by 3 times the cubed root of x. So when we multiply that by 0, we get back 0 is equal to, when I distribute it to the right-hand side, that clears my fraction. I'm going to distribute my 2, so this gives me 2x plus 4. And so when I distribute it over here, though, that gives me plus, I have a 3 outside of my radical, but this gives me a cubed root of x times the cubed root of x squared. Same index, we can multiply underneath, so that gives me a cubed root of x cubed, which just is x. So combine like terms, it's a linear equation. I get 0 is equal to 5x plus 4. Isolate my variable, I get negative 4 is equal to 5x. So x is negative 4/5. And so this is also a critical number. So I need a test to see positive or negative, or not positive, sorry. I'm used to teaching you where is it increasing and decreasing first before we do this, but we haven't done that. So we're going to plug these back into our original to see what type of value we get. And our original function was y is equal to, sorry, x to the 2/3 all times x plus 2. So if we go back in and we plug in 0 into that original function, well, 0 raised to any power is 0, and 0 times anything is also 0, so we have a point at 0, 0. And now if we go back in and we plug in negative 4/5 wherever we see an x. Okay, so remember that is the cubed root. So we're going to look at the cubed root. I guess you can leave it as power if you want. If you put it in parentheses, negative 4 divided by 5. And then you're going to raise it to a power. Put the power in parentheses, 2 divided by 3. And then we're multiplying that whole thing by negative 4/5 plus 2. Eeks. I got domain error. Let me see what happens.
I got 1.03.
1.03?
Yeah.
Okay. So looking at that, we can see that that's going to be a max occurs at -4/5 at 1.03, and a min is going to be 0 when x is 0.
Did you get negative or did you get positive?
Salvador, positive or negative?
I
Or
got a
actually, it should be
positive.
negative. Shouldn't it be negative because it was a
I got a negative.
4/5 is going to be.
Oh,
a
yeah.
negative.
It's negative, sorry.
Wait. No. Wait a minute. -4/5. Because actually you're squaring -4/5, right? And then you're taking the cubed root of it. Or if you took the cubed root of -4/5 and then square it, that's positive.
Yeah, because I just like I put down the whole like original equation into my calculator, and for the x I just put -4/5, and I got
So
a positive.
it should be positive.
Yeah.
That's positive.
So this is the max, and this one was the min. And so basically what we're going to be looking at is we can tell where the graph is increasing and decreasing. We can start plugging things in on the left and the right of what we just found our critical numbers into the derivative to see if the derivative is positive or negative. If the derivative is positive, and this is what you're going to look forward to seeing. I'll write it down later. But if the derivative is positive, we know the graph is increasing. And if the derivative is negative, we know that the graph is decreasing there. And if it was equal to 0, we have it leveling out. So it's like a horizontal constant at that point. And so that's what we're going to probably start looking at either tomorrow or Thursday. So that was 4.1, and I think I got through all of it, but I will make sure I did. And if I didn't, I will finish up what I missed tomorrow. So I'm going to stop the share. I'm going to stop